Good afternoon, everyone. So my name is James Torre, and my talk today is going to be on using Racket to investigate a combinator calculus, the Nock combinator calculus. And I'm going to try to get across how I used Scheme to deeply investigate the process of converting the informal specification for Nock into two implementations, and what that means for the use of the calculus in its actual applications, which are predominantly in industry. Now, I say in industry, but very small industry. So just going to jump right into it. This is what the Nock combinator calculus looks like. If you're familiar with the SK combinator calculus, or with the Y combinator, or with Curry's combinator, which is like four combinators to it, this is rather more featureful, shall we say, but it's more complicated. And it's meant to be an intermediary between minimalism and practical affordances, specifically to support functional systems-level programming. In addition to the academic interest, which I have in this, there are a couple of, again, uses in industry. Urbit and its descendants, which are network-centric operating systems, Zorp, which is a zero-knowledge virtual machine company. Some of the ideas in Nock have been used in other projects. Simplicity by Russell O'Connor, which is a functional blockchain language. Owlon Blue, which is a very interesting reactive demand programming model out of David Bombor, which I don't think exists outside of his WordPress account. And then there has been some previous work in doing deep academic analysis of Nock. I refer specifically to Edward Amsden's subject knowledge analysis for optimized compilation, and Richard Hjort's Nock, which is a K-framework implementation out of University of Illinois Urbana-Champaign, I believe. But independent of the claim of whether it is capable of supporting rigorous practical functional systems programming, there is the question of whether or not this spec, which is given in a combination of natural language and pseudocode, can be fidelitisly transferred into implementations which can work in rigorous environments like blockchain, like zero-knowledge proofs, like a functional operating system. So my goal is not to give a tutorial on Nock, but to jump into what some of the choice points are in implementing this spec. But I will draw your attention to a couple of things. So we see on the middle left-hand side of the screen the / operator. And those operations are tree indexing. They are a way of accessing portions of a binary tree. So if the combinator calculi are theories of binary trees, then in Nock you have access to the indices of a binary tree directly. You note that there's no need to do any sort of church encoding for natural numbers. It's just assumed that that is an implicit available to you. And then on the right-hand side, there's a whole host of star reduction rules. And these are different evaluations of different structures of Nock expressions. Also up top, you see that it says Nock 4K, which stands for 4 Kelvin. One of the idiosyncrasies of the design of this system is that, much like Donald Knuth's tech program, the versioning has a limit. It doesn't go on forever. As with Kelvin temperature, you go down to 0, and that's absolute 0. With tech, it limits to the value of pi. At some point, all bugs become features, and the specification is frozen. So it is indeed important that if you come across this 50 years from now, when it's a frozen specification, and you have no other extra systemic knowledge of what does it mean to implement the Nock calculus, can you do it from a spec? What does a compliant implementation look like? Where are your choice points? And so the first choice point is to ask, well, what is a valid Nock expression, a valid NEXP at all? There's a little bit of framing language at the top of the spec. A noun is an atom or a cell. An atom is a natural number. A cell is an ordered pair of nouns. Okay, this is just describing binary trees. And then it says to reduce. Okay, so we've got some reduction rules. By the first matching pattern, variables match any noun. Okay, so then you have a choice of how are you actually going to represent your binary trees of natural numbers. In Nocksche, which is the scheme implementation, okay, that's straightforward. In Nocko, which is the relational programming implementation, because it uses the native miniKanren reverse binary numbering system, I introduce a tag for the natural numbers, so that way a string of zeros and ones doesn't look like a Nock expression, but is instead identifiable as a natural number inside of Nocko, and thus inside of miniKanren. But yes, so a valid nexp. So by a strict interpretation, this is all that you get. If you are writing Nock code, this is what you have to write. But there's a distinction we see between that external syntax of nested pairs of natural numbers and all this internal syntax, which nevertheless is used in the course of evaluating a Nock expression. And so you have and there's no indication that any of this is enclosed within the other, reduced by the first matching pattern. Perhaps we're able to simply write a question mark AB or a star expression. So if you want to expose the internal syntax as part of your interpreter, is the first choice point that you have to make. And for debugging purposes, it's much easier to expose the internal syntax, to be able to not have to thread through from your Nock entry point, the NOCK keyword, whatever else it is you want to do inside of your, whatever else it is you want to test inside of your interpreter. All right, well, the next question is, I said the Nock keyword, but is Nock a keyword? Is it a prefix operator like the /, the plus, the star, the equal sign? Or is it the indicator for what is it your main? Is it does it sit outside of any Nock expression? So this comes on the question of, are you going to have a runner function like eval, a neval, which will take a quoted Nock expression, or are you going to have your operators themselves be functions directly? And so at the top, we see here that defining neval, and in fact defining interpreters for Nock in general, when you have the affordances of scheme, are quite straightforward because it's just pattern matching. And so you import match in Racket, and then you can construct the reduction rules using quasi-quote. And when you're inside of miniKanren, miniKanren has native pattern matching, so you can do a straightforward translation of your scheme implementation to a miniKanren translation. Notably, though, if you're going to have a runner function, an eval for Nock, then you have to wrap, you have to make explicit where execution continues, where there is another reduction to be performed. Which you can then, you see in the first line here, that we essentially do a term rewriting from tar of A, B, C, D to neval of tar AD, which is the first star pattern. But you can eliminate the explicit calls to n eval if you then instead have tar, which is the shortened version of star, as a function directly. There are questions about the semantics of the specification, specifically strictness. So at the bottom of the star rules, we see that there is evaluation which is performed, which then doesn't seem to refer, or evaluation which is performed on the left-hand side, which doesn't seem to refer to values on the left-hand side. So your patterns, the patterns that you're matching, then produce something which ignores the b value. So do you need to care what b is? If b is non-terminating, does that mean that the expression as a whole needs to be non-terminating? And this is probably, like from an academic standpoint, the most significant thing which the spec does not tell you. One is informed by the use of this calculus in the systems which gave rise to it, that yes, you are actually concerned with the value of b. You do have to evaluate it. You do have to, if it does not terminate, have the entire reduction rule not terminate. This is because this particular set of reduction rules is used as a hint to your underlying interpreter, rather underlying virtual machine. So if you had something which was evaluating Nock expressions inside of a purely functional environment and you wanted to communicate to the outside that there was some sort of side effect that needed to be performed, then this b value is where you would introduce that hint. So if the calculation of what that side effect should be is itself non-terminating, then the reduction rule as specified, the two rule 11s, should also be non-terminating, and so in fact, Nock is a strict calculus. The other interesting case is the final rule, this star A to star A, which, if nothing else matches, then produces an infinite loop. You do, in fact, need to identify that it's an infinite loop and then perform some sort of out-of-band interrupt. And this becomes especially interesting when we start looking at the differences between, using Nock to investigate the differences between a Scheme implementation and a miniKanren implementation. Because while Scheme is a functional language, miniKanren is a pure relational declarative language. And in a pure relational declarative language, the order with which clauses evaluate is non-deterministic. There must be a full partitioning of your possible pattern match space so as to produce the effect of match from the first pattern downwards. In a functional language like Scheme, you effectively get the conjunction of negations of every pattern which did not match above a given pattern. So I'll repeat that, jumping back up to here. Reduced by the first matching pattern. Okay, so if we have some pattern which we're matching, if we're using the match macro, then if the first pattern does not match, and the second pattern does, that is as though the second pattern had been whatever it says, plus and not the first. The third pattern is whatever it says, and not the first, and not the second. You fall through the pattern match. In a pure relational language, you don't have that natural gravity, and so instead you have to explicitly partition your pattern match space. Because otherwise, star A to star A can match anything which precedes it. Those are all valid patterns. And so then you could have an arbitrary runtime, or an arbitrarily long trace of your miniKanren interpreter running, even though eventually it might make progress. But there's no guarantee as to when exactly it makes progress. And according to the natural language, the plain reading of the spec, you must reduce by the first matching pattern immediately. All right. So there is a little bit of additional grammar to a Nock expression. So it's binary trees, but it's right associative binary trees. And we are informed that it's a right associative binary tree by one of the early rules, which shows us that the three-element tuple, ABC, becomes the two-element tuple of A and the pair BC. Okay. When does this happen? Is it shallow or deep? Are we just going to take a look? Like, should our interpreter just see, okay, am I 3 elements, and then I'll group the rightmost 2? Or do I need to recurse through A, B, and C and produce a fully normalized right associative binary tree? Do you have to do it at all? Could you, like, is this rule, where it's present in the list of reduction rules, even necessary? Could you do it inside somewhere else in your implementation of the other operators? Imagine as though you had come across this on Desert Island or 50 years from now, and there was some pile of USBs that you wanted to then write an interpreter to run the code which was on it, but all you had was this spec. What would you write? What could you write? Would you converge to the same answer as the individuals who wrote their Nock interpreters 50 years ago? To give the answer here, I interpret this, and most of the Nock implementations that I've encountered interpret this as basically more natural language, and that informs you that yes, you should recurse down a given Nock expression, ensure that it is a fully normalized right associative binary tree. If it's using Nock internal representation syntax, that is, if it has the pluses, forward slashes, stars scattered about, then you should also recurse inside of those and perform the appropriate normalization. So, not that hard to do in either Scheme or miniKanren. Nocksche and Nocko both have their appropriate functions or relations to perform this right associativity. Actually, and so show of hands, this is the Scheme workshop, and so I'm going to focus on that implementation, but are folks familiar with miniKanren? Okay, very good. Reverse tree forth. So once you have an interpreter for Nock, then you start getting to play around and get a sense of like, what is it like? What is the nature of this combinator calculus? And Anton Duden once called Nock reverse tree forth. And forth being a stack-based language, when you have things like functional stack-based languages, like kitten or factor or joy, then you have stack combinators. So you can think of Nock, and not just think of it, does have tree combinators, and the reverse aspect is that in comparison to, e.g., the SKI combinator calculus, instead of being left associative, it's right associative. So we see here that there's no direct Nock equivalent for the I combinator. That's okay, because I combinator is superfluous. There are, through a simple syntactic transform, K combinator equivalents and S combinator equivalents. And then curiously also the Z combinator equivalent, and the Z combinator is the strict Y combinator. So you essentially take, like, if the combinator calculi which we are familiar with are prefix left associative, then the corresponding rules in Nock are infix right associative. And so you can write definitions for I, K, and S, and evaluate equivalence within Nock of the I, K, and S combinators. And even if you had, regardless of what your concerns might have been as to the computational universality of the calculus, this demonstrates that yes, in fact, it's universal. You can define S and K, and from there build any computation you so desire. We'll note that, like the unlambda esoteric language, these particular K and S combinators are curried, or they require obligatory currying. That is the C suffix there. And so you then, in turn, have to explicitly mark using the star operator when you want evaluation to proceed. So in the unlambda SOLang, you use backtick, and in this implementation of the SCI combinators in Nock, you wrap each application of the combinators in star for eval. Okay. In addition, so insofar as presenting novel contributions to the field of computer science is concerned, in addition to these being, as far as I know, the only Nock 4K Scheme and miniKanren implementations, this is, again, as far as I know, the first implementation of a quine in Nock. And if we have time, I'll go to the appendix and I'll break down how you derive this quine. But what I want to draw attention to is that if we look at its at the Nock expression in the first line, it's only using the zero reduction rule, the zeroth reduction rule, and the zeroth reduction rule is the tree index reduction rule, which shows that giving explicit access to the calculus of its own structure, or of the structure of its own code, makes it quite straightforward to construct self-referential programs like quine. And at the very top, you see star A to star A. There's also the trivial quine, however, and an infinite number of trivial quines, if you allow as valid Nock expressions the internal syntax of star, a series of natural numbers that don't match to any other pattern. Well, the Nock will produce that same input as its output, and it will produce it again and again and again and again and again. And then it becomes a question of whether you want your semantics to be, is an infinite loop an output? Have I in fact provided my interpreter with an input that has produced an output where the input and output are identical, when that output is going to be consumed again as the next step of an unending computation. So these are things which, when you just look at the specification off the bat, it's not clear what the correct answer should be. And so as you are implementing, and as I was implementing the language, these questions came up. And I found it to be useful, specifically having the trivial means of implementing the Nock reduction rules in Scheme to then play around with, okay, what does the correct Nock interpreter feel like? So at the GitHub link on the bottom left, you will find both these slides and also a link to all of the ramblings that produced these slides and their content. This is just an artifact extracted from them. But there's a couple of pieces of future work which I would find interesting to pursue. One is just the puzzle, almost, of generating more combinators, showing that the translation of, for example, Curry's BCKW combinator calculus into their Nock equivalents. There is something in the official Nock documentation which says that rules 6 through 11 are reducible to rules 0 through 5. So the last star reduction rules are reducible to the first star reduction rules. I've never seen that done explicitly. It would be cool to demonstrate that. Although the quine here, the quineo, does work in Nocko, it only works in the forward direction and to verify that input in fact does equal output. I have yet to be able to get it to do reverse synthesis. I think that using Clojure's core logic over the over finite domains would have better luck with that, because then you could essentially cap the size of the numbers that the reverse synthesis search has to search. Then, if you're going to have a universal computational model, you need to have the universal computational model implemented itself, so Nock and Nocko would be cool. And additional formal verification would be very cool as well. There was a initial effort by this fellow in Coq, but the couple of talks on formal verification and visualization today I'd be very curious to apply them to these investigations. References to various things in the talk are here, and this is the quine derivation, which we can go over perhaps over lunch, but I'm free to take any questions. Thank you for your time.
All right, we have time for a question or two. How would you say so did you come up with the scheme or the miniKanren implementation first? And kind of what inspired the differences, I guess, when you were exploring these?
So the scheme implementation was actually second from the miniKanren interpretation, though then after I wrote the scheme implementation, I went back and rewrote the miniKanren interpretation because it was much easier. I think I went the hard way around first, writing it in miniKanren, but then once you had the scheme, then the standard translation from functional to relational programming applied almost everywhere.
Thank you.
Okay, thank you so much for your talk. This is not my area of expertise, but I would like to know how much effort does it take to do this kind of stuff, because it's impressive.
So the specification of Nock is intended to be straightforward to implement. And if you just write out the reduction rules, then yes, it is quite straightforward to implement. But because in the process of just writing out the reduction rules, there were these lingering questions about how to tighten up what the spec actually means, that is what makes it an ongoing project, in fact. There are plenty of very performant, or I should say more performant than my naive implementations as used in the Urbit, Plunder, et cetera projects. But I'm still kind of curious, like, if it's meant to be a frozen standard, are there edge cases which will come around to bite the projects further down the line due to the, again, as far as I know, lack of full formal specification?
All right, let's thank the speaker again, and then we'll break for lunch.